For this project, we're going to be introducing a fun peripheral on the Go board, the 7-segment display. Let's get started talking about how a 7-segment display actually works. You've probably seen 7-segment displays in a huge number of places in your life, anywhere from an alarm clock to a vending machine. If you pay close attention, you'll realize that 7-segment displays are everywhere. And normally you see a 7-segment display that just counts from 0 to 9, like this GIF is doing over here. But, they can actually count in hexadecimal all the way up to F pretty conveniently. Here, watch. A, B, C, D, E, and F are all possible combinations, and you can even make up things that are not even real numbers. There are a lot of combinations of ways to light up these displays. Normally you just see 0 to 9. But this is what a 7-segment display actually looks like. Each one of the segments, there are 7 of them, are labeled A through G, according to this figure here, A, B, C, D, E, F, G. So if, for example, you want to illuminate and draw the number 1, you would illuminate segments B and segments C. If you wanted to draw the number 0, you would illuminate everything except for G. So that's basically how they work, and for this project we're going to make use out of these fun peripherals. Before we get into the details of the project, though, we should talk about how the encoding scheme works for 7-segment displays. So I downloaded this table from Wikipedia, and I find this to be extremely useful for just, rather than trying to figure it all out yourself manually, 1 is B and C. Okay, 2 is, the following, and trying to draw it all out. Go to Wikipedia and just pull up this table here. It's located at this URL that I put on the bottom. It's convenient because it shows you, if you pay attention to this column here, A, B, C, D, E, F, G in this order. To draw a 0, it's 0x7e. So 7e is 1, 1, 1, 1, 1, 1, 0. The only digit that's 0 is going to be digit G. And for drawing a 0, like I said previously, G is the only one that's not illuminated. So this hex encoding here, 0x7e, maps specifically to the digit 0. 1, 0x30 means that, well, based on the way I would look at this, I would imagine that only B and C would be illuminated. 3 is 1, 1. 0 would be 0, 0, 0, 0. So B and C being 1, 1. Let's take a look. Oh, yes, that's what a 1 looks like. B and C are illuminated. So if you go through this column here, you can actually do a kind of a lookup-based approach where your input is a digit and your output is this hex encoding right here. And that's what we're going to be using for this particular project. So I'll show you how that's done. I should state that if you've never seen this 0x before, this is a representation for hexadecimal. So 0x7e is a hexadecimal representation of a number. Okay? So let's talk about this project, what this is going to be doing. The purpose of this project is to increment a binary counter to drive 1 digit of the 7-segment display each time a switch is released. So in the previous project, we built the debounce filter, which incremented or toggled the state of the LED every time the switch was released. Now we want to do something a little bit more advanced where every time the switch is released, we're going to be incrementing a binary counter, and that binary counter is going to be displayed on our 7-segment display. So every time you push the button, you're going to see the 7-segment display count up from 0. 0 to 1, 1 to 2, 2 to 3, 3 to 4, etc. And it's going to wrap around when it gets to 9, wrap around back to 0. We're only going to be using 1 digit of the 7-segment display. If you feel ambitious and you want to count past 10, you're more than welcome to try that, but this project is just going to be an introduction to the 7-segment display peripheral, and we're only going to be using 1 of them for this one. So I'm going to get started with the Verilog implementation of this. This actually isn't too bad of a project, so if you want to give it a shot on your own, I definitely recommend it. If you're a little bit stumped and you want me to talk through my solution, keep watching for the Verilog solution first, followed by the VHDL solution. For the Verilog section, let's get started with the binary to 7-segment conversion. So this is going to be a file that takes in a 4-bit binary number and converts it to 7 segment outputs. So I'm going to call it binary to 7 segment. And there's going to be, we can have it clocked or not clocked, but let's have it clocked for the sake of it. Input 3 down to 0, I binary num. So for the record, the binary input is going to be a 4-bit binary input, and there's going to be a bunch of outputs. O segment A followed by B, C, D, E, F, G. Let's change these. Okay, and that's what our module looks like. Not too bad. Well, that's the port for it anyway. Now we're going to be creating an intermediary signal. I'm going to call it, it's going to be a 7-bit signal, and I'm going to call it hex encoding. And I can just default the value to zeros for now. And this is going to be the encoded value of the input binary number based on this table here that I showed you previously from Wikipedia. For this, I'm going to be creating an clocked always block, which we've seen before. Always at pos edge clock. Love it. Begin. And now I'm going to be introducing a new construct from Verilog that we haven't yet seen called a case statement. So case is a keyword, reserved keyword in Verilog. Open parentheses, I binary num. So what this is doing is, if you've seen a case statement in C, it behaves exactly the same way. But basically, it allows you to specify the different cases or ways that I binary num can be represented and do things based on the input I binary num. So for example, this makes sense when I show it to you, but 4-tick B0000 colon. So this line says, for the case in which I binary num is equal to 4-tick B0000, so I binary num is all zeros, do something. And in this case, I want to set the R hex encoding value. I can put this on a new line, or it can be on the same line, doesn't really matter, but R hex encoding gets set to 7-tick hex 7E, like that. So 7-tick H, I guess I haven't really talked about this yet, but the 7 means it's going to be 7 bits wide. Tick is an indication of the type that's coming after it, so H represents a hexadecimal number, and in this case it's going to be 7E. So 7E, if you were to convert that to binary, would be 111 1110. So this is 111 is 7, 1110 is E. So hex encoding is set to 7E for the case in which the input binary number is equal to 0. So if you look over here on this table, that makes perfect sense, because when your input binary number is 0, we're going to want to set the hex encoding value to 7E. Let's look at the next one. Now I want to set this to, I'll give you a second to think about it. What do you think? 30? That sound good? 1 is my input digit. Here's 1 right here in my case statement. And for that particular case in which I binary num is equal to 1, set hex encoding to 30. We'll do one more. For the case in which it's equal to 2, our hex encoding gets set to 60. Oops, 7-tick H 60. I'm going to pause the video here and just complete this file and show you the results. Alright, I completed the case statement. I did move the hex encoding onto one line just to make it a little bit more compact. And then down here I also added some assign statements where I broke out each individual segment based on this table here. So hex encoding bit in position 6 gets mapped to segment A. hex encoding bit position 5 gets mapped to segment B, 4, C, etc. all the way down. And that's what this table is showing here. A gets mapped to the most significant bit, B is the next one, C is the next one after that. So now we have a module where if you give it any input binary number, it will correctly do a lookup table based approach. This is called a lookup table, where you give it an input and the output is based on some lookup, some combination, some lookup combination, some table. And we can drive any 7-segment display. For this project, we're actually only going to be using combinations from 0 to 9, which is here. We're not going to be using 10, 11, 12, 13, 14, or 15, which is A through F. But the nice thing about this module is that if you ever do need to access A through F, it's already built into this code. So this is really important because it really allows your modules to be flexible, portable, and reusable. If you need a binary to 7-segment converter anytime in the future, all you do is instantiate this module and you're good to go. You never need to look at these details ever again. So portability and reusability is extremely important, and that's what makes VHDL and Verilog so special, is that they allow a good degree of reusability. I'm going to move on to the higher level module now, where we actually instantiate this binary to 7-segment. Alright, I've written the code for the top level 7-segment display, and I'm just going to talk through it rather than typing through it. For the top level module, we've added the O segment 2 underscore A underscore B. These names are important. These names get mapped to names that are on the pin constraints file, so make sure that you match these names exactly when you do your code. Let's see. We also introduced a new reg, which is 3 down to 0, which represents our 4-bit counter. So we initialize it to 0, and this is going to be the one that counts up every time the switch gets hit. We have some intermediary wires here, which will map the output of the module we just created to the outputs up here. We'll see down there how that looks. But basically all this is doing is it's building on the exact code we did previously. We still have our debounce switch filter in here. W switch 1 is the debounced output of the switch filter. We're still registering it inside this clocked always block, and we're incrementing the count now when the switch is pushed down. Previously this was just the line where we were toggling the state of the LED. Now what we're doing is we're actually incrementing a counter. So when the button gets pushed, it'll do a simple check here that just says if the current value is equal to 9, set it back to 0. Otherwise, increment the counter by 1. And that's going to be, this R count is going to be the input to our 7-segment display, binary to 7-segment display module that we just wrote, which is right here. Here we go. Binary to 7-segment is the module we just created, inst is the instance name, and then we do the mapping of all the signals. We give it a clock, we give it the input ibinary num is now our R count value, like I was just saying, and the output is mapped to this intermediary signal W underscore segment 2 underscore A through G. The reason I have to create an intermediary signal here is because the output is actually an inversion. This little tilde is an inversion of the wired signal. And the reason this happens is just the way that the Go board is created. Rather than driving the 7-segment display segment high to illuminate it, you're actually going to be driving it low to illuminate it, just based on the way that it's wired up. So you do need to invert the signal before you drive it to the output, but that's it. So this code now will increment the 7-segment display, segment 2 display, every single time the switch 1 gets pushed down. That should do it for the Verilog code. I'm going to be moving on to the VHDL code next. You feel free to skip ahead to building the project. Alright, for the VHDL section, I'm going to get started first with the binary to 7-segment conversion, which is the lower level module that we're going to be instantiating at the higher level module. And we're going to do our favorite lines, library, IEEE, standard logic, 1164.all. entity, call it, well, you can call it whatever you want. I'm going to call it binary to 7 segment. And you could make this clocked or not clocked if you want. Actually, this doesn't really matter. But I chose to make this particular module be a clocked module, so I'm going to give it a clock input. That's personal preference. Could have gone either way on that one. So there is going to be a binary number input, which is going to be 3 down to 0. And there's going to be a bunch of 7-segment display outputs of type standard logic. So let me put those all in. Let's fix that. B, C, D, E, F, and G. There we go. Oops. So what this module is going to be doing is taking in a 4-bit binary number, which is a standard logic vector 3 down to 0, and doing a lookup based on this hexadecimal encoding table here that I showed previously to drive these 7-segment displays, these single-bit outputs appropriately. Let's define our architecture. Give it a name like RTL. And there is going to be an intermediary signal here. I'm going to call it hex encoding. The type is going to be standard logic vector, 7 down to 0, and we'll give it a value, a default initialization value of others to 0. Ooh, have we talked about others down to 0 yet? So others equals sign greater than sign 0 with the little single quotes around it means take the array of bits here, 7 down to 0, and assign all of them to 0. So that's what this means. It's a little weird to look at, but this is the way that VHDL sets an array of bits down to array of bits to 0. You can do, yeah, so that's usually how others is used for the most part. Now we're going to create a clocked process, or a sequential process with a sensitivity. The sensitivity list is just going to contain the clock, iClock, begin, and our favorite if rising edge iClock. Then do something. What are we going to do? So here's where we need to implement the hex encoding table here in VHDL. So this is going to be introducing a new VHDL keyword, which is the case statement, which we haven't seen before. But if you've ever used C or Java, it behaves in pretty much the same exact way. So binary num is going to be the case statement, the input to the case statement. The way the case statement works is it says, looking at this input signal here, when it's of a certain value, do something. So we need to specify all the combinations of this particular input in this list of whens. So when binary num is all zeros, it's an array of zeros, then we got to do something. In this case, I want to set our hex encoding to 7E. And this X quote 7E means hexadecimal. This is a hexadecimal assignment. This is saying take an 8-bit vector and assign it to our hex encoding, which is also 8 bits. So that's the first situation here, and you can see that 0x7e is what we see when the digit input is 0, which happens here when binary num is equal to 0. We can do it as well for binary input of 1. We have to go through all of these actually. Our hex encoding now gets set to, looking at the table, 30. And we'll do another one. Our hex encoding get set to, this one is 6D. You are going to need to go through every single case for the input binary num 0 to F. I'll just skip that part and show you the results. Alright, I've assigned all the possible values of R_hex encoding based on this table here. And down at the bottom, we do need to actually assign the outputs, which are O segment A through O segment G. And if you look at the table, A corresponds to the most significant bit of the R-hex encoding, which is bit 6. Hex encoding bit 7 is actually unused, so we don't really care about that one. You can just drop it, and the synthesis tools will remove it. Segment B corresponds to bit 5, segment C corresponds to bit 4, and that's based on this table look up here. That's what this table is telling you. And now that's it. So now we have a binary to 7 segment module. The nice thing about this module is that if we ever need to use a binary to 7 segment converter ever in the future, we can simply instantiate this module. Now this particular project only counts from 0 to 9. We don't actually use 10, which is here, 11, 12, 13, 14, or 15, which correspond to A through F. But the nice thing is that this code is here should we ever need to use a project where we need to count all the way up to F. So that's the nice thing about creating something once and making it pretty versatile and pretty reusable, is that you only need to create it once and you can instantiate it in many places. So now that you see how the binary to 7 segment conversion works, I'm going to be creating the top level of the project, which will instantiate this module that we just created. Okay, rather than show you line by line how this code is created for the top level of the project, I just will talk through it quickly. So we do need to use numeric std, which I believe was on the previous project too. That's for the counter value, so that we can actually increment a counter. We do also have new signals added to the top level entity. So we have our input switch, I_switch1, and then O segment 2 _ A through G. Segment 2 is the lower digit, segment 1 is the upper digit of the 2-digit 7-segment display on the Go board. This project is making use of the lower digit, so we can simply just use those. These names are important. These names map to the PCF, the pin constraint file that we've used previously, so make sure that you get these right. So if we skip down here, let's see. We did add a new signal called R_count, which is of type integer, and we give it a range 0 to 9. So we want to count from 0 to 9, which makes sense. And I also created some intermediary signals, which I'll show how those are used. The debounce filter code is exactly the same as the previous project. W_switch1 is the output of the debounce filter, and it's the filtered version of the switch input. We're still registering that particular signal and looking for the situation where the switch is pushed. And when the switch is pushed, let's see, this one is looking for the situation where the switch is pushed down, actually. So this is actually not looking for the release of the switch, it's looking for the push of the switch. Either way, code functions the same. When the switch is pushed down, R_count, it'll check the value of R_count. If R_count is equal to 9, it'll reset it to 0. Otherwise, it will increment the counter by 1 every single time we detect that the switch has been pushed. Here's the instantiation of the binary to 7-segment converter, which actually drives our display. And we give it a clock input, the same clock as we've been using. You do have to do a little bit of a conversion here, because R_count is of type. Okay, so this is probably worth talking about. R_count is declared up here as type integer, range 0 to 9. So how do we convert something that's an integer to something that is a 4-bit standard logic vector? VHDL is very strongly typed. It can be a little intimidating for beginners because it'll throw all sorts of compile errors. And it can be a good thing in that it's harder to make mistakes as a beginner because the syntax checker will not let you even compile code if the types don't match. But it's also really frustrating because you can bang your head against the table and sometimes the errors are a little cryptic, so you have no idea why it's not compiling correctly. So this is one of those situations, in which I could see you getting hung up really easily if you're not familiar with this. What this is doing is it's calling a function toUnsigned, and the function toUnsigned takes the signal that you want to convert, which in this case is an integer, and it converts it to something that's called an unsigned type. I'm not going to get into the details of what unsigned is right now. I think that's for another lesson. But basically just know that signals can be signed or unsigned. You know what? I'll mention it. Unsigned signals means that they are always positive. Signed means they can be positive or negative. So this is going to be an unsigned signal, and the 4 indicates it's going to be 4 bits wide. There's another conversion wrapped around this, which is converting that unsigned signal to a standard logic vector type. Standard logic vector doesn't have any inherent signed or unsignedness, so again, the actual number is exactly the same whether or not it's signed or unsigned. It's just that VHDL is very strongly typed. So if you have, like for example, 1001 and it's of type unsigned, that is not the same as standard logic vector. Even though you look at this thing and you go, well, it's 1001, it's 9. Who cares? 9 is 9, right? Well, no, not in VHDL. 9 can be 9 in the unsigned world. It can be 9 in standard logic vector world. And then you can also say that that's not the same thing as signed. So this is just a little introduction to how VHDL can be a bit of a bear. You'll get used to it. I did. Take some time. So this is a 2-type conversion of the arc count signal. And now everything's happy and it'll compile. The output of the binary to 7 segment are the individual segments here. And I do route them to individual wires because they need to be inverted down here. And the reason they need to be converted is just the way that the 7-segment display works on the Go board. Normally the LEDs that we've been using have been active high, where you drive it to a 1 and it illuminates. The 7-segment display is the opposite of that, where you have to drive it to a low for it to illuminate. And the easiest way to do that is just to put a little inverter right on the output. So this will add another lookup table right on the output here. And now O segment 2 _ A through G will correctly drive the 7-segment display. That's it for the VHDL section. I'm going to go ahead and build this project and we'll take a look at the results. I have added the project 7-segment top, the binary to 7-segment file, and the debounce switch files to my project. And I have run through synthesis and I've run through place and route at this point. I'm just going to go ahead and crack open the synthesis report, scroll down to the bottom just to take a look to see what we've used so far. Now we're starting to get up there in some resource utilization here. 31 register bits total, so 2% of the FPGA, still got lots. And we've used 3% of our LUTs lookup tables, 51 lookup tables altogether. Neat. Let's also look at the output of the place and route, which is the timing file that we want to look at here, just to see what our clock signals look like. So my design says that it found the signal I clock, and the target was 25 megahertz, which was pulled in from the constraint file, and the signals were able to map at 192 megahertz. So plenty of headroom on this particular design. We're able to run many times faster than our desired clock. So as long as this number is bigger than this number, we're good. We have no timing errors, and the FPGA design should work correctly. So let's go take a look at the programmed Go board and make sure that it's behaving the way we want it to. Alright, the Go board has been programmed, and now you can see when I push down switch 1, the 7-segment display is counting. 6, 7, 8, 9, and then it loops back to 0 again. So the project was successful. Now, 7-segment displays are a lot of fun, and I just showed you how to use just one of the 7-segment displays on the Go board. So there's a lot more projects that you can do here. I think you should, try to get creative here. Maybe do a project where you have a millisecond counter and you can count to see how quickly you can, or a reaction counter where, an LED lights up and you have a certain amount of time to push a button, and it'll tell you how long it takes you to push the button in milliseconds, for example. Or you could do a 2-digit counter. The world is your oyster when it comes to what you can think of to do with a 7-segment display counter, but they do make projects a bit of fun. Having that visual feedback is definitely nice. So I definitely think you should take some time here, maybe do some extra projects on your own, get more familiar with either VHDL or Verilog, whichever one you're learning, and get familiar with 7-segment displays because they're pretty neat. The next project is going to be talking about simulation inside your FPGA, which is a new concept, and we'll get started with that next.